Good morning. Last class, that means last few classes, we were discussing about the carbon to carbon migration of alkyl groups or aryl groups. Carbon to carbon migration of alkyl groups or aryl groups. Now, in this class, we are discussing about the migration of alkyl groups or aryl groups from carbon to nitrogen. That means here we are discussing carbon to nitrogen migration of alkyl groups or aryl groups. Carbon to nitrogen migration. Okay. In this class, the first rearrangement is Hofmann rearrangement. Hofmann rearrangement. So, the first rearrangement that we are discussing coming under carbon to nitrogen migration is Hofmann rearrangement, and let us see what is Hofmann rearrangement. When an unsubstituted amide is treated with sodium hypohalite will give a primary amine contain one carbon less than that in the starting amide. This rearrangement is known as a Hofmann rearrangement. What is that? When an unsubstituted amide is treated with the sodium hypohalite, will give a primary amine. That primary amine contains one carbon less than that in the starting amide. So this is a very simple rearrangement. In a simple way, we can say that the conversion of an amide into a primary amine, conversion of an amide into an amine, that amine containing one carbon less than that in the starting amide. This rearrangement, the rearrangement occurring in this reaction, that is what is known as a Hofmann rearrangement. So look at here, when an unsubstituted amide is treated with the sodium hypohalite, will give a primary amine contain one carbon less than that in the starting amide. So what is that? What is Hofmann rearrangement? Amide RCONH2 is treated with the sodium hypohalite NaOX sodium hypohalite. What will give? You get amine like this RNH2. You can see that RCONH2 and it is converting to RNH2. That means amine is containing one carbon less than that in the starting amide. Okay, now let us go through the mechanism of this Hofmann rearrangement. Look at the mechanism. Hofmann rearrangement. Okay. RCONH2 is treated with the sodium hypohalite. Example, we are taking NaOBr. NaOBr means Br2 plus NaOH. Br2 plus NaOH means sodium hypobromide, or we can write it as Br2 plus NaOH, followed by hydrolysis H2O, followed by treatment with water hydrolysis, we get RNH2. So now we are going through the mechanism. Look at here, C double bond O NH2, correct? And our sodium hypobromide Br2 plus NaOH. Here we are taking Br2, that means Br, correct? That means delta plus, delta minus, you can see that this lone pair electron in the nitrogen atom will attack on this bromine, and okay, correct. This paper we actually have studied. The lone pair is attacking on this is delta positive, and this bromine is delta negative. Positively charged bromine, the lone pair is attacking, and we are getting R C double bond O NH2. NH2 can be written as a NH, and it is joining with the Br, and nitrogen is getting a positive charge. Correct? And what will be minus Br minus, minus Br minus, minus Br minus. Okay, it will be there. So the lone pair is attacking on this bromine, and you are getting RCO NH2 Br. That means since the lone pair is making a new bond, and the nitrogen is getting a positive charge. Now you can see that in the next step for stability, you can see that this NH bond, okay, okay, for stability, minus H plus removes a proton, and it will change into R C double bond O NH Br. N bromamide, N bromamide. In the N position there is a bromine, so N bromoamide or N bromamide, N bromoamide. Okay, N bromoamide. Okay, this up to this step it is very clear. So for stability minus H plus, and it is changing to RCO NHBr. Now look at the next step. Okay, this R C double bond O NHBr can be written as NHBr. Correct? Same only RCO NHBr. NHBr is written as NHBr. Now our base. See, look at it here, Br2 plus NaOH. Br2 is used up here, and you can see that our base OH minus is there. This OH minus removes this proton, because this proton is acidic proton, and it is removed, and you can see that this pair of electron is shifted to nitrogen. Okay, this proton is removed, and this bond pair electron is coming to nitrogen, and you get R C double bond O N minus Br, N minus Br. Okay, and what is eliminated? Minus H2O, minus H2O, R C double bond O N Br. Now in the next step, this is very clear. Okay, in the next step you can see that the resonance stabilization. Okay, this negative charge is shifting to here. Negative charge is simultaneously what is happening? This bond is moving to oxygen. Okay, and we get R C O minus double bond N Br, double bond N Br. Okay, and in the next stage also it is very clear. Okay, this is shifting to here, or now look at here very carefully. In the next stage you can see that now in the next stage you can see that this is a concerted mechanism. Everything that means this is a concerted mechanism, single step reaction. When this electron comes back, you can see that, look at very carefully, this alkyl group migrate from carbon to nitrogen, and the same moment the halide ion will be eliminated. This rearrangement is important. So look at it here, when this negative charge comes back to here, so what is that? Then the same moment the alkyl group breaks from this carbon, and it is migrating to nitrogen. The moment what will happen, the leaving group is removed from nitrogen, and we get, since R is joining with the nitrogen, I am starting with R is joined with nitrogen, En, then there is double bond C, then what is that? Double bond O. This is alkyl isocyanate, alkyl isocyanate. Alkyl isocyanate. Actually, this rearrangement is known as Hofmann rearrangement, formation of alkyl isocyanate. This alkyl isocyanate on hydrolysis will be converted to the primary amine. So once again, you look at the mechanism of Hofmann rearrangement. Amide is treated with sodium hypohalite, followed by hydrolysis. We are getting a primary amine. That amine containing one carbon less than that in the starting amide. And look at the mechanism, the lone pair of nitrogen is attacking on Br2 molecule, and you are getting this structure for stability minus H plus, and you are getting N-bromamide. Now this N-bromamide, this proton is removed by our base, OH minus is removing our proton, then it is changed to nitrine ion, nitrine. This is okay, and you can see that when for stability, this negative charge is shifted to here, O minus. Now in the next stage, when this comes back, you can see that the alkyl group is migrated from carbon to nitrogen. The same moment our leaving group is expelled and we are getting acyl isocyanate. Okay. Now, this alkyl isocyanate, actually the formation up to this rearrangement, this entire rearrangement is known as Hofmann rearrangement. Now, alkyl isocyanate RN double bond C double bond O, when treated with water, look at it here, you can see that the lone pair of oxygen is attacking on this partially positive carbon, then this bond is shifting to nitrogen. So, you are getting RN with a minus charge, okay, and C double bond O, OH2 can be written as OH, H with a positive charge, correct? H2 is attacking on this carbon, the bond is shifting to here, so you are getting R, since the bond is coming to nitrogen is getting a positive charge, and you can see that OH2 is attaching, OH2 is attaching, and oxygen is getting a positive charge, and of course the double bond O. Now you can see that for stability, this, okay, 1H plus, okay, this bond is shifting to here, that means minus H plus, and that H plus is attacking on this negatively charged carbon, that means minus H plus and plus H plus. Okay, now minus H plus and plus H plus, look at it here for stability, this proton is removed, and you can see that this proton is attacking on this negatively charged nitrogen, and we get what is the structure? R, NH, C, double bond O, OH. Okay, this is the structure R, C, NH, C, double bond O, OH. And in the next step, there is another rearrangement. I am writing the same thing like this. You look at it here, R, NH. Okay, in the next step, you look at it here very carefully. You can see that in the next stage, look at it here, this bond, OH bond, okay, this breaks, and this bond is shifting to here, this bond is breaking, okay, and shifting to nitrogen. Again, you can see that here is H plus is removed, minus H plus, and that means here it will become C double bond O, minus H plus, and when this bond is shifting to here, nitrogen is getting a negative charge, and that means minus H plus and H plus, that proton is accepted by this nitrogen, plus H plus, what you will get? You are getting RNH2 plus what is eliminated? CO2. Correct? This is the last mechanism. Water molecule is attacking on the alkyl isocyanate. What is this one? Isocyanate. Water molecule is attacking on the alkyl isocyanate, so it is attacking on the carbon, the bond is shifting to nitrogen, okay, for stability, minus H plus, that H plus is taken by nitrogen, so it is like this, RNH, OH, double bond O, then there is a rearrangement, the OH bond breaks, okay, then this bond is shifting to nitrogen is getting a negative charge, and you can see that that the removed proton is attaching to the negatively charged nitrogen, and it will be converted to RNH2, and the CO2 gas is evolved out. So this is what is Hofmann rearrangement, that is the conversion of amide to amide. Now let us go through another example, little bit complicated example. Suppose your compound is like this, look at it here. Okay, and your reagent, one is ammonia NH3, second one is Br2 NaOH, followed by hydrolysis. And what could be the product? Now, look at the reagent. So, how will you know that what type of rearrangement is occurring in this compound? So, you have to look at the reagent. So, there is ammonia, and you can see that followed by sodium hypohalite, and of course, this compound react with ammonia, it will be converted to amide. it will be converted to amide. Amide is treated with sodium hypohalite. Definitely the rearrangement is Hofmann rearrangement. That way you have to understand what type of mechanism is involving in this particular reaction. So let us go through, let us check what will be the product. So look at very carefully. This is our starting compound. Okay, double bond O. Here it is double bond O, correct? First we are taking NH3, okay, NH3. Look at here, the lone pair electron of nitrogen, lone pair electron of nitrogen. That lone pair electron is attacking on this positively charged carbon, correct? NH3 is attacking on this double bonded carbon, okay? And you get, so it is like this, okay? Here no change, double bond O, correct? And here it is, you can see that it is like this. And when it is attacking here, it will become O minus, and it will become what is that, NH3 is there, or you can write NH2H with a positive charge, correct? Since lone pair is attacking, nitrogen is getting a positive charge, NH3 is written as NH2S. Now you can see that for stability, you can see very simple step. Okay, this goes back, this bond pair electron. So minus H plus, H plus is removed from here, and that H plus is attaching to oxygen, and you are getting minus H plus and plus H plus. What will be the product? You can see that. Okay. Look at here. It is like this, and here it is double bond O. Here it is O, and you can see that here it is like this. Okay. Here it is. It will become OH, and here it is NH2. Is it clear? So minus H plus, and that H plus is attaching to the negatively charged oxygen, and you get like this. And in the next step, you can see that in the next step, okay, look at it here, you can see that this OH can be written as, now you look at it here, if a carbonate atom is having OH, this type of 1,1 diol. 1,1 diol is there in the same carbon. You can see that what will happen. The H, okay, this type of rearrangement is there. This bond is shifting to here. Then what will happen? This bond is breaking. That means it will change into C double bond O plus what will form H2O. This type of rearrangement will occur if the carbon is having a 2 OH group like this. Then what will happen? The bond breaks, and what is that? H plus is removed. That H plus is going with when this bond is coming with here, the bond breaks from carbon. That means OH minus is going with the H plus, and it will change into H2O. Similar type rearrangement will occur here. Look at here, this OH, and here also this carbon is attached to OH, and this side also you can see that another O. Okay, so you can see that the same rearrangement OH. Okay, OH, it can be written like this. Then what will happen? This bond will be shifted to here, and what will happen? This bond breaks from here to here, and what will happen? And you can see that H plus is removed, minus H plus. That H plus is attaching to this negatively charged plus H plus, correct? And what you are getting? We get a structure like this. Okay, here it is like this. Okay, double bond O. Here it is OH. And you can see that here it is a double bond O, and what is this one? NH2. Correct? This is the action of ammonia. First step is over, and what you are getting? You get, look at this structure, RCONH2. This part is taken as RCONH2. This is an amide. Now you know that amide is treated with sodium hypobromite, and followed by hydrolysis. Definitely the rearrangement is Hofmann rearrangement. So look at the first reaction. First reaction is the action of ammonia. Ammonia is attacking on the positively charged carbon, and there is a rearrangement, and you are getting minus H plus. That H plus is attaching to this oxygen. Here it is OH, and this carbon is attaching to this O and another O. And since there is a rearrangement like this will occur, this bond is shifting to here. That means minus H plus. Simultaneously, this bond is breaking, and oxygen is getting negative charge. This H plus is attaching to the negatively charged oxygen, and you get amide. Okay, this is the first step. That means reaction of this particular compound with the ammonia. Now look at here. So what is our compound? You compound like this. Okay, we got an amide, double bond OH, and here it is double bond of NH2. Okay. Now our regular, what is that, Hofmann rearrangement. Next step, as we have studied, Br2. That means Br. This lone pair is attacking on this Br. Okay, minus Br minus, Br minus, and we get here. Look at here. It is like this: double bond O, OH, and here it is a double bond O. NH2 can be written as NH, and you can see that there's Br. Okay, NH2 Br. NH2 is written as NHS, and since this lone pair is making a bond, and it is getting a positive charge, correct? And for stability, as we have explained earlier, minus H plus, proton is removed, okay, and we get what we are getting. We get you look at it here. We get a structure like this, okay, correct? Okay, it is like this: double bond O. Here it is OH, and you can see that double bond O, NHBr, correct? This positive charge is removed, minus H plus, and it is changing to NHBr. And in the next step, look at it here. In the next step, what is the next step? Again, I am writing the same structure. The same structure I am writing. Ring. Okay, double bond O, OH, and here it is double bond O. NH can be written as NH, and here it is Br. Correct? Now you know that what is that? Our base. Now the base is coming, this base, so I am writing the base is here, OH minus. As we have discussed earlier, OH minus removes a proton, and this pair of electron is shifting to nitrogen. Okay, so minus H2O, minus H2 is eliminated, and we get the structure is like this. Okay, correct? And here it is double bond O, OH, and here it is double bond O. What is that? NBr with a negative charge. N is having a negative charge. It is a negative charge. This is our nitrogen, N minus. Correct? And in the next step, what is happening? This negative charge is moved to here. Okay, then this pair of electron is moving to oxygen, migrating to oxygen. And you can see that what we are getting, we get a structure like this. Okay, look at it here. Here it is no change. Double bond O, no change. OH. Okay, and here it will become O minus, and here it will become double bond N, and Br. Correct? So nothing new, as we have discussed earlier. Okay, only take this part as this part is taking as a R. Correct. This part is taking as a R, RCO, NH2. No change. Okay, we are continuing. So our structure is now like this. We have reached here. Here it is like this. Double bond O, OH, and here it is. Here it is O minus, and double bond N and Br. Okay, this is the structure. Now look at here as what is the next step? When this negative charge goes back, you can see that what is that here. If this is the entire part is R, in the general mechanism, what is happening? When this comes back, the R is removed from here, and it will attach on this nitrogen, and the bromine is eliminated. Same way, what is that? This bond breaks from this carbon, and it will attach to nitrogen. So what you will get? I am starting with the nitrogen is here. Okay, wait a minute. So this entire thing break from here. From here it is breaking and is attaching to nitrogen. So I am writing like this. So here it is like this, no change. Double bond OH, and what is happening? This bond breaks from here and is attaching to nitrogen. Of course, nitrogen is there. And what is that? Double bond C. Okay, here it is C. Okay, C is here. Okay. So this bond is breaking and attaching to nitrogen. So attaching to nitrogen, double bond C, and since this pair of electron double bond O. What is this one? isocyanate. What is this one? Isocyanate. Okay, now in the next step, in the isocyanate, what do you know that is reacting with water? Okay, reacting with water. H2O. How it will react with water? Okay, this what is that? This lone pair is electron is attacking on this carbon, as we are discussed earlier. So what will happen? This bond is shifting to nitrogen. So you are getting structure like this. What is our structure? Okay, here it is. Ring is here. No chain, double bond OH. Okay, here it is N, and with a negative charge C, double bond O. You can see that OH2, that means OHH. That means positive charge. Okay, now you can see that what is that for stability? Minus H plus, this bond is shifting to, okay, that means minus H plus, that H plus is attaching to negatively charged nitrogen, and we get the structure like this. Okay, here it is like this, double bond OH, and you can see that here it is NH, and here it is COH, and here it is double bond O. Correct? Okay, nothing new. The proton is removed from here, and what is it? It will become OH. That removed proton is joining with the negatively charged nitrogen, and you get like this. And in the final stage, what is that? As we have discussed earlier, this OH bond, this bond is migrating to here, shifting to here, coming to here. Then what is that? Then that time what will happen? This NC bond, this will break, and so what will happen? Here also minus H plus, this H plus is removed, that H plus is attaching to this nitrogen, and plus H plus, what do we get? We get a structure like this. You see that C double bond OH, and what is here? Here it is NH2 plus CO2. See, amino benzoic acid. This compound is forming. So what is the product here? What is the product here? You can see that the product is okay, C double bond OH, NH2. Amino benzoic acid. So this is a particular example for Hofmann rearrangement. Hope you have understand the basic rearrangement happening in Hofmann rearrangement, and thank you.